And we were talking about Gibbs free energy, right? And we related that to enthalpy of the system as well as entropy of the system, right? So delta S and delta H were both involved. We connected them relative to a system and put it into the context of delta G. We saw that delta G equals delta H minus T delta S, where T then is going to be a determining factor whether or not something is spontaneous, right? Because the delta G was an indicator of that spontaneity based on whether or not it was negative or positive, right? If delta G is negative, then I have a spontaneous process within that system is how I'll describe it, okay? That we were able to derive this through finding this, if you recall. So another indicator of spontaneity is delta S of the universe, and delta S of the universe on its own, if it's positive, would be spontaneous, right, of a system, and negative would be unspontaneous. But since you have the delta T here all wrapped up into the delta G, then therefore when delta G is negative, it's a spontaneous process. Are there any questions on that? This delta G was called Gibbs free energy. Ultimately, what that means is that in a system, I have different thermodynamic properties occurring. I have enthalpy, which is heat for the most part, and I have entropy, which is more disorder or less, okay? And in those combinations, I can end up getting a certain amount of either putting in energy to the system or energy out of the system. So if I get delta G here, if I get some energy from it, then I could use that energy to do what we called work, if you recall, in an earlier chapter. Okay? So that gives me the opportunity to do work based on the energy I gain from Gibbs free energy or delta G. So that's why it's called free energy. I could harness this energy and then convert it into work for something. Okay? And that would be called W max. But of course, most systems I cannot get the maximum amount. I'm going to lose some to the surroundings, which therefore would increase the entropy of those surroundings, right? And I would only be able to use a little bit of that free energy for something. And that's sort of the overall point to where we're getting at. The one other thing we're going to talk about is that most of these things are going to be talked about in terms of specific states, right? I'm going to give you states and then you can correlate across. But then, of course, not everything happens in the standard state. So we'll talk a little bit about non-standard states as well. Very similar, if you want to put an analogy to it, to gases, right? Where we talk about ideal gases versus non-ideal gases, right? Ideal gases are under certain conditions and non-ideal gases are under slightly different conditions. And there was an add-on term associated with that from van der Waals, if you recall, right? So you had the different PV equals nRT, and then you had the P and the V had extended terms that were added on for non-ideal conditions. So we're going to do something very similar. We'll look at standard conditions of delta G, and then we'll look at non-standard conditions, and that's how we'll finish up the chapter. Okay, so hopefully we put this usually more complicated chapter into something more manageable, right, which is the objective. So I just wanted to recall where we were at, where we stopped. And hopefully when you were here Tuesday, you wrote good notes to how we ended up getting this and what it all means.
Yeah.
So this is not that big of a, we're going to get back to this slide, I think, a little bit later when we talk about a system and we talk about the equilibrium of that system. And you can see here at the lowest part of this curve here, this is, so how much do I want to talk about this? Okay, let's say you have these as reactants here, and this is your product, and you're in some sort of equilibrium. So what I really want to say is this is your system. The system in this case happens to be a chemical reaction, but that is your system, right? It doesn't necessarily have to be a chemical reaction. I could also use just liquid to gas or something like that, right? Which wouldn't necessarily be considered a chemical reaction. So I'm going to call this my system. If I look at this curve here, and we're going to talk a little bit more about this kind of thing, but here's my free energy, and here's my direction of the reaction going this way. So here would be my products, these would be my reactants. At the lowest point of the free energy, that's where I'm at equilibrium. That's all that's represented. Okay. So if I set delta G equal to 0, I have 0 free energy. I'm at equilibrium in my system. Of course, it could be a chemical reaction, and in this case it is. But I still want to emphasize, I think it's better to think about it as a system, and you're not as confused if you're just going between, say, gas and solid, or liquid and gas, or whatever else. Okay. If I'm somewhere here, which is my, remember we determine these by reaction quotients, and I'm not at that equilibrium, then the reaction under these conditions, whatever they may be, ideal or non-ideal, depending, then if I would move this way, would be moving towards my spontaneous movement of this system to the equilibrium. And if I'm over here, then the spontaneous direction would be going back down that way. That's just something you've already experienced with the Q's, right? That would be, where's the reaction quotient relative to the equilibrium constant? If it's above it, then you'd go this way. If it's below it, you'd go this way. So this is just putting in Gibbs free energy in the context of a system that has some level of equilibrium, and where you are in that equilibrium is another way to think about where you would go in terms of the spontaneity of that system. What direction am I moving towards? Okay. Like I said, I'll revisit this a little bit later. I also want to point out when I'm talking about delta G, I'm talking about the delta G of the formation of the two NH3s as a gas, okay? And that should be a question that you come up with, because when you see it in this format, you would say, well, okay, well, this would give me a negative delta G going this way. This would give me a positive delta G. So why would that be spontaneous? And the point there being that I'm moving this direction relative to this. So that means that if I flip this and I'm now looking at it that direction, my delta G is negative going down. Okay, so make sure that that's clear. I might get into that a little bit more when we get into non-standard state conditions. But this delta G that's moving through here is referencing the movement from here to here, right? So therefore the delta G should be negative going this way, and it should be positive going this way under certain conditions. But once I get to a point over here, now it's going to shift it this way, and now I'm looking at a delta G going from this direction to this direction. Hence, then, once again, going back down would be spontaneous because my delta G now would be negative, but for the inverse of the system, in this case, of the reaction. Okay? Okay, so let's summarize this. Here, okay, reaction, delta, so when delta G is less than 0, it's spontaneous. I've emphasized that over and over and over. When delta G is greater than 0, it's non-spontaneous in the direction that I'm referencing, so that's also really important. That's what I just pointed out in that earlier slide. Product favored, reaction here, the reactants are favored. Forward reaction, I don't know why that's any different. Okay, delta G is a composite. Okay, so you can get delta G from the delta S and the delta H of the system. Okay, and that's something we put together on Tuesday. So there's nothing new there. This is just a summary of those things. So this is kind of saying the same thing. This is really important here. And I will add that I just want to re-emphasize, there are two ways that I showed you how to get spontaneity of a system. Delta G is clearly one of them. The other one, as I pointed out to start this lecture, was delta S of the universe. It's just a more awkward way to do it. But if you see it, delta S of the universe, you can also assess the spontaneity of that system based on that. And that would be if it's more positive, as opposed to delta G is more negative. I just want to once again re-emphasize those things. Okay. Any questions on this up to here? No? Okay, we're going to do another part that I've already gone over. And that is looking at 4 different cases in referencing Gibbs free energy in the context of delta H of the system and delta S of the system. Remember, those are both of the system. So if you weren't here Tuesday, maybe look at one of your peers' notes, because when we looked at all of this and derived this, which I thought was really important, we were able to assess the differences between universe, system, and surrounding, and what the complications of those things were. And then as we work through, so as you hear me, whether if you were not here on Tuesday, you might not fully appreciate why I'm saying this is of the system and this is of the system, right? And I think you should make sure you know that. That will wrap it up and make this whole section a little bit easier for you, okay? Okay, so if I look at this equation here, and I say delta H is negative, and delta S is positive, what is going to be my delta G, positive or negative? I'm not looking for specific numbers, I'm just simply saying, is it positive or negative?
If H is negative and S is
H is negative,
Yeah.
S is positive.
negative.
The overall delta G will be negative. Everybody see that should be pretty straightforward. If the overall delta G is negative, is it a spontaneous reaction?
Yes.
That's it. That's case one. Okay. So reaction is spontaneous at all temperatures. Doesn't matter what the temperature there is, right? It would make no difference if delta H is negative and delta S is positive. Once again, delta H of the system now is negative. That means that it reduced energy, right? And delta S, just to make sure we understand what we're talking about, delta S of the system is positive. That means it had more spread out, more entropy at any temperature. Overall, the delta G, which another way to think about this is the delta S of the universe has now increased. And therefore, it's a spontaneous reaction. Okay? Or the system is moving spontaneously. Okay. That's another way to think about it. So in case one, when delta H is negative, delta S is positive, blah, blah. Now, if I look here, there's my delta H and that's negative, and I say something delta S is positive, whether I don't even know whether I put that in there. I'm going to now do the next one. Delta H is positive, delta S is negative.
So
The delta G will always be positive. It will always be what? Non-spontaneous. Okay. Independent of the temperatures. Temperatures don't matter. So the first two cases are very easy. This next case, delta H is negative. Now delta S is also negative. So now the temperature does matter, right? Because if delta H is negative and this is also negative, that makes this whole term positive. So I want this term to be as low as possible, which means the temperature, the lower the temperature, right, the more chance I have of it being spontaneous, absolutely. So at low temperatures, delta G, which means spontaneous, and positive at high temperatures, because now this would be a higher number than this, and therefore the overall delta G would be positive. So in those circumstances, when the temperature is lower, then I'll have a spontaneous reaction. When the temperature is higher, then I'll have a non-spontaneous reaction. So that's case 3. So reaction is spontaneous only at low temperatures. Okay. And lastly, I now have delta H as positive and delta S as positive also. And in this case, once again, now I care more about delta T being higher or lower? Higher. When T is higher, then I have a spontaneous reaction. When temperature is lower, I have a non-spontaneous reaction. So those are so positive at low temperatures, negative at high temperatures. That's another way to translate at high temperatures it's spontaneous, at low temperatures it's non-spontaneous. Okay. And that is essentially all wrapped up here. Okay. So that's what the debating method that walk you through each one of those or just take you here. But I like that you did actually show the equation so you could quickly assess it. Okay. And once again, we actually talked about this on Tuesday, if you recall. Right? We had dialogue with you guys. You asked about this and this. We talked about low or high temperatures, and this is basically the table that represents all of the different scenarios that you can have as a result of having high or low temperature and you could say the sign of the delta H and the delta S. Okay, so when it's plus minus, it's spontaneous. And here's delta H, delta S, plus minus spontaneous, plus minus non-spontaneous, negative negative. Then it matters about the temperature. So at low temperature, it's spontaneous. High temperature, it's not. And a plus at low temperature, it's non-spontaneous. At high, it is. Okay, so it's all wrapped up right there, nice and easy. All right. Is that okay? It's always easy when I'm doing this, right? Okay, let's take a look. Predict the conditions: high temperature, low temperature, all temperatures, no temperatures. That means under which each reaction below is spontaneous. So what are they giving us here? We have to have something like this. Okay. So what about this one? Delta H is negative, delta S is negative. So let's first eliminate that not at all temperatures, right?
Yeah.
Right.
Spontaneity means delta G has to be negative. I know my delta H is negative. So that means I want my delta S to be the lowest positive possible. Since delta S is negative, remember there's a negative in front of that, makes it the overall term positive. So that means that at lower temperatures, this would be spontaneous, right?
Right.
Yeah.
Okay. Okay, this time I won't help. You guys tell me.
Spontaneous at high temperatures.
Yep. Janet, and I heard Mona, I think. Spontaneous at high temperatures. Is it given in there? No, it's just not easy, right? Too bad it's not that easy when you're taking an exam, right? It's a little bit more juxtaposed within the memory.
She said, "Don't take away her credit."
Well, no, hopefully it stays that way. Right? Ideally, it stays just as easy.
Let's hope.
What about this one? High temperature, I heard? Okay.
And you were gonna be given the change of H signs, right? Because we're not given them in the book.
Yeah. Yeah, it just shows the equation.
It just says the equation.
But it doesn't say delta H or delta S.
delta H. It says this is endothermic though.
Hold on. I could do a couple things. I don't want to just say yes or no, because if I just say yes or no, then I don't leave any room for anything else. I have to give you some form of the delta H. I could give that to you though in multiple ways, right? I could either say delta H is negative something or positive something, and then that's pretty easy to assess the plus or minus. In other words, it doesn't have to be given like this. I could also just add a plus heat over here, some energy, or plus energy over there within the chemical equation, which means now you pull it out as delta H as either endothermic or exothermic. So I could do a variety of things. Those are all things that you know. So just saying yes or no to your question, yes, you will get some form of being able to identify what the delta H is. But you may not just get it as this form. So it's just keep that, you know.
And even calculate it as well, or no?
What's that?
Even calculate the energy, or no? Like to calculate the delta H using.
Can you? You may. You could.
Okay.
That could.
Like
Absolutely.
constant pressure, whatnot.
By having standard state conditions.
Right.
And then having the chart for the delta H's and under standard state conditions or something like that. You could.
Okay.
Right? Less likely in this kind of question.
Right.
But in a more extensive question,
The
it
background
could. Yeah.
questions,
Yeah.
okay.
And the delta H here, can you determine this on your own?
That's nice. Okay.
Because of the moles of gas.
Because of the moles of gas.
Right.
Absolutely. 2 moles of gas, 3 moles of gas.
Right.
Is this going to increase entropy or decrease going this way?
Increase.
Increase.
Right.
Delta S is plus.
Mhm.
So once again, just to make that clear, I don't have to give you it this way, even though I'm doing it here, just to clarify the concept, right?
Yeah.
But on an exam, you've got to put those things potentially together depending on how I represent either of those two terms.
So just then you figured out the delta S
Why?
entropy because you looked at the moles. Could you figure out the
Delta
delta
S?
H? Just like-
No,
It goes with
Yeah,
moles.
you had found out you could-
So what is more?
you have to have something.
So more moles
Yeah.
means more.
So if I put a,
Oh, okay.
go
For
ahead.
part C, it says endothermic in it.
So that
And that would tell you right away that this is positive.
Yeah,
Yeah.
it's gaining heat.
So I could just say it like that, right? I may not say anything. I mean, there are multiple ways that you could determine what the delta H is in terms of its positive or negative characteristics, right? And I just gave you a whole bunch of different ones. So that's why it's not such a straightforward yes or no question. I don't want to set you up and say, oh yeah, I'll give you the delta H, and it doesn't come out in this form, and now all of a sudden you're like, wait, where's the delta H? Right? There are multiple ways that I could represent you determining the charge on the delta H plus or minus. Okay. None of them are that challenging. I just don't want to throw you off and have you expect that you're just going to see it like that. You may,
Yeah,
but you may
yeah.
not. Okay. I also don't want to limit what I put on the exam and how I present it. Okay, what do we have here? For the reaction shown below, calculate the, okay, so here it's specifically asking to calculate the delta G and determine if it's spontaneous. If the reaction is not spontaneous at 25 degrees, since you're checking this at 25 degrees, which is 298, right? Determine what temperature, if any, the reaction becomes spontaneous. I like this question. And here you're given directly, here's just delta H and here's delta S. What do I do and what do I need to be careful with in a problem like this? The units, thank you.
Units.
Very good, Alex. So this is kilojoules, this is joules. delta G equals delta H minus T delta S. So I'm gonna be putting these two things together, so these things have to match.
Yeah.
Okay, so keep that as Alex pointed out the units, that's important. And do I have everything? This is really kind of a simple problem.
Mm-hmm.
Yeah, right.
Yeah.
By the way, you notice this is in Kelvin, so what does the temperature need to be in? Kelvin. Okay, so it's just, all I'm looking at is 95.7 minus 298 times this, and I can either convert this to kilojoules or I can convert this to joules, right? It's just a 1 to 1,000 factor. So if I converted this to it, it'd just say 142.2, and I would say, what, 1,000 joules per 1 kilojoule, so I'd divide it, so it'd be 0.1422, or this times 10 to the minus 3, or whatever else I want to, however I want to do it, okay, just to make that clear. So, of course, this is the equation. Let's put this in. So there's my 10 to the minus 3. All I did was convert the joules to kilojoules. There's my 298. I multiply the kelvins cancel. I multiply the kilojoule, or add the kilojoules after I multiply this here. I get this. I get plus 53.3 kilojoules. Very simple calculation, right? At this point for you guys. But now I need to assess this. A little bit different with delta G's here in general, because now I say, okay, I have the delta G. What does that mean? Right? So in a lot of cases, in math classes, before you took 1065 and et cetera, you basically just determining numbers, right? You're doing calculations with numbers. Then you get in your first chem class, and then you go through multiple chem classes, maybe a couple bio classes, start to get into physics. And now you're starting to put these numbers into calculations that have units, and what does it mean in terms of that respect. So that's essentially now where we've put things in with units and we understand what it is we're referencing. Now there's an extra component here. Now that I have the number, I now understand that delta G deals with 53.3 kilojoules. So the kilojoules means it's an energy. That's that extra component beyond math. But now I also have to say, well, that plus, and what does delta G mean? That plus means that in terms of free energy, I have none. And therefore, this is a non-spontaneous reaction. So now I'm taking it a step further. Instead of just doing the math, and then just figuring out what that math can translate into from a calculation, I now have to look at what I get as an answer for the calculation, and then say, what does this mean? Right? Does everybody follow that, how we're progressing and how we interpret things? So delta G, if it's a positive, means that it is non-spontaneous. There's no free energy available. Okay? So if I go back to here, it said determine whether the reaction is spontaneous, and I was just able to do that, and it's not. So then it says if the reaction is not, which kind of is a clue that it probably wouldn't be right, in any test. I mean, it could be, but it's highly unlikely they wouldn't include this. Then it says determine what temperature, if any, the reaction would be spontaneous.
So you gotta play around with the temperatures.
So now what would I want to do? This is really, really simple when you think about it.
You just plug it in.
I definitely want to increase the temperature, or is that what let's double check this, right? So I want this to be higher here.
Yep.
But how do I determine where it would be spontaneous or not? What is the criteria here for spontaneity?
It's negative.
When this is negative.
Mm-hmm.
So if I set this equal to what?
Any number.
Negative 1.
Closest thing.
What if I just set it equal, so let's see specifically what it's asking for. It's not saying anywhere. It's saying determine what temperature the reaction becomes spontaneous. So I can't just plug in anything there. Zero, absolutely. And what is zero in relationship to that other chart we looked at a little earlier? That's the equilibrium of the system, right? Everybody see that? Okay, so then I set this equal to 0, and I still have this number and this number, so what am I now solving for? The temperature, and that will tell me where this system will become spontaneous. Does that make sense? Easy? Okay, good. Okay. So I'll go look at, make sure that you know this. Okay, so at equilibrium, 0. Solve for t, so that's just subtract, divide by negative delta S. You get this kind of thing here. I still have the same numbers here and here. I put those on top of each other. For whatever reason here, I'm just showing you I converted this to joules, where up here I converted this to kilojoules. Does not matter which one. They just have to be consistent, right? And I get 673 Kelvin. Does that make sense to our earlier discussion about the 4 scenarios, where I had a positive delta H and a positive delta S? That means that at high temperatures, right, that it should be spontaneous. And 678 seems pretty high. That'd be a high temperature. So it fits the criteria for all of our knowledge in how these things work. So that seems like a pretty reasonable number. If it happened to be really low, you'd say, well, wait, something's not right here, right? Okay. So this is okay for everybody? Cool. So how's this section doing? Usually this part of the class is very challenging. I've tried to find all kinds of ways to make it easier.
So when we have to find the temperature and stillness, we spontaneously always set it to 0.
I'm sorry, say that again?
When we're looking, so for instance, like it's asking, it asked if it's spontaneous or not, it came out that it's not spontaneous. So to try to find the temperature at what?
It would be spontaneous.
So we
Where,
always equal it to 0
Yeah.
at that?
because that's where you're at equilibrium. And remember, when delta G is negative, it's spontaneous. So at 0, then what's the next thing it's got to go to? Got it, something right
That's
there.
204 degrees Fahrenheit.
Okay, which is pretty high, right? So this particular system would not be spontaneous
Yeah.
unless I was at these conditions, this temperature. Okay.
Would it matter the amount of moles with temperature? Like the higher
What do you
moles
mean
you
by
have of gas, the higher moles of gas that you have, you actually require more temperature than at less moles of gases? In a system that has like higher moles, for example, in the product side.
They gave you the delta S and delta H, so it changed those numbers. It wouldn't change what we did.
So you're looking at the molar ratio of in this case, the balanced chemical equation,
Okay.
right? So if you have a greater mass or a lesser mass, which therefore could translate into a greater amount,
Okay.
then you would have to account for that in some way. That we're just saying that if you look specifically at this chemical reaction, which is balanced, and the balancing here is important.
Yeah.
Because yes, if, here the 2 moles here, if I'm looking at something that's being made
Mm-hmm.
and it's 2 moles, then I have to account for that 2 moles under standard state conditions, let's say,
Right.
right?
Mm-hmm.
But in this scenario here, just as Taylor said, you're given the delta H and the delta S, and that's in relationship to this. It's
Okay.
already given. If I had to solve for this, and I had to solve for that,
Mm-hmm.
then you've done that, right, with delta H.
Yeah.
If I put the delta H into standard state conditions and you had to solve for it,
Mm-hmm.
how would you do it?
Using for the Q, for the
Delta H,
Uh-huh.
and solving for delta H, how would you do it if I said it was under standard state conditions and you had an appendix 2 probably in your, or B or A or whatever it is in your book, and it gave you the list of all the delta H's of formations of each thing, how would you solve for the delta H here?
Oh, you take the sum of the
Yes.
products minus the sum of the reactions.
Sum of the products minus the sum of the reactants, and in that, do you deal with the moles?
Yes.
Okay.
Yes.
Right.
Okay, is that okay?
Alright. Yeah.
Okay. Okay, so, and here we go. We're gonna talk about standard states. Okay, now, in Chem 101, we did talk about delta H in standard states, right? And that's what Dieter just recited how to solve for it. When you have that, you take the sum of the products minus the sum of the reactants, including the moles, based on the molar ratio in the balanced chemical equation, right? But, can I also do that for delta S? And delta G? Yes, I can do that for any of them, right? If you recall, and if you were in my 101, I actually let you know that, by the way, here's delta H, and if you look at the other 2 columns that you didn't talk about, delta S and delta G. So now you know all 3 columns. And you could solve for any of them the same way, exactly the same way.
Okay.
Okay? You just have to make sure that you're defining what the standard state is, because not everything is in a standard state. And if it's not, we'll talk about non-standard states a little bit later. So the standard states are defined as, if you we would call pure gas pressure, exactly 1 atm, and this is going to matter a lot in non-standard states. If it's a liquid or solid, they're
180.
pure substances in their most stable form when the pressure of 1 atm and the temperature is at 25 degrees. Okay. And lastly, in solution, the concentration is 1 molar. Okay, these are the standard state conditions. So if I say standard state, we've got to remember, I'm at 1 atm and 298 Kelvin. Okay. So, we're just going to simply do this thing here. S minus S products minus S reactants gives me the change in the reaction. Blah, blah, blah. What do we want here? Okay, so, So this, once again, same thing as you saw with delta H, no big deal. In fact, you see with anything delta, right? If you have a delta here, what does that mean?
A change.
Right, this is very familiar. That's just the products minus reactants or the final minus the initial. No big deal there. But what I'm going to point out here is the standard molar entropy of the substance is measured against the absolute value of 0 as defined by the third law of thermodynamics. So the new part here, if you haven't had physics, is the third law of thermodynamics. Okay, and that's essentially that the entropy, so that's the delta S, right? The entropy of a perfect crystal at absolute 0 is 0. That's it.
No entropy.
What this is really leading you into, and the point of this, is that when we look at things for delta S, we're looking at things just like the delta H. You're going to have different components. So if I have, let's say, an element, the element itself should be 0 of these things, right? But if I have it in different physical states, is it going to be 0 still? No. In other words, is the gas of, say, oxygen going to be the same as the gas of a liquid? I've said the water or the H2O is a liquid or the H2O is a solid. They're all still in their basic states. Or let's just say oxygen. Oxygen, gas, liquid, solid. Would the entropy be the same for all of them? Even though it's in its lowest state? No, there will be slight differences. So the one at 0 or the one that's the most stable, that's what's going to be the 0. So you could have different amounts of each. So therefore, you really probably won't have very many at 0, right? Because they're not at absolute 0 ever. And we're looking at these in the standard states at what? 298
Right.
or 25 degrees, right? So this is just letting you know, though, that the lower it is, the closer to 0, the closer it's perfect, the less you're not going to have any energy associated with it. That's all. Okay? So this is the only way to arrange these crystals. I'm not going to really, once again, no, I'm not going to ask much more than that about this, if even that. Just kind of an intellectual idea that I want you to know. Okay. Now, looking at molar entropy, we're looking at what has the lowest amount of entropy and what are the conditions that you could assess to determine if something will be lower in entropy than something else. Okay, so and I'm talking about entropy here. So if I say the entropy of helium is 126.2 and the entropy of argon is 154.8, is there a way, if I didn't know these numbers, that I would be able to quickly say that argon should have a greater entropy than helium?
Size.
And there are 3 different types of criteria that I want to bring up, or maybe 4. I'm going to label it's not labeled this way in the text, but you could literally write 1, 2, 3, 4 comparison between things to determine the entropy of them, whether one's higher or lower than the other. The 4 criteria are the molar mass, and I'll walk you through each one. The molar mass, the state, or I should say the physical state of the substance, the molecular complexity, which I'll explain, and the extent of dissolution. In other words, separating if you put it into water. Like, for example, the dissolution would just be if I take sodium chloride as a solid and I put that into water, I clearly get sodium plus chloride minus. Okay. What's that?
More entropy.
Yeah, this would be more entropy. So then that would translate actually just to say NaCl aqueous. This would be a greater entropy than this. Okay. So now let's look here.
It's right there.
So, okay, this is
Oh, you
odd.
have your-
All right. So the first thing is the physical, you got the physical state of the substance, but the first thing they talk about here is the molar mass. Okay, so let's organize what this slide is showing. It should go 1, 2, 3, 4, or A, B, C, D, or something like that. It doesn't do that. So the very first criteria here, well, let's just talk about molar mass. As you increase the molar mass, you increase the entropy of that thing. Okay. Most things I'm going to give you a rationale for. This is a little more complicated. I guess the one thing I can say, if you have more molar mass, what does that mean? That you have more what? Yeah, but more specifically, it looks like they're showing me all. What are these? Compounds or elements or?
Elements, yeah, no.
They're all elements. So in this context, the molar mass of elements. So the reason I'm pointing that out is because there's no molecular complexity to it. They're all just one thing. Okay. So in that context, where there is no molecular complexity, then by increasing the molar mass, I'm literally increasing what?
Atoms,
The most?
protons,
Protons and neutrons. Do electrons factor into the molar mass?
Oh, no.
but
No.
if you increase your protons, you
Well, I'll get to that, but I asked about the molar mass, what's literally increasing, not electrons, right? With the molar mass. That has nothing to do with the mass, just the size. If I'm increasing the molar mass, therefore increasing the protons and neutrons, now what else am I increasing? And now you are answering my question, more electrons, obviously. If I have more electrons in a system, they're more compacted in there, and then the energy levels are smaller and more of them. So therefore, with more energy levels, more energy movement, more energy dispersed, greater entropy. Hence the general basic concept of the idea. You need to know that, not necessarily. What you need to know, if I increase the molar mass, I increase the entropy of it. Simple. That crosses off this one out of those 4 things. Okay. The next one is this. This kind of flips, right? So the physical state. This is the easiest of them. This should be blatantly obvious, right? A liquid versus a gas. The gas is going to have more entropy of the same thing, and it clearly does. This is S. That's it. Nothing more to it. The physical state, solid of one thing. And so this is also a little bit of something I want to point out. The first thing we talked about were just different elements relative to each other, masses. The next thing I'm talking about is the same thing, element or compound, and in that same thing, its own states. Okay. So here you're looking at solid, liquid, gas. The gas is going to be the most entropy, the liquid would be the second most, and the solid would be the least of the same thing. Go ahead.
Is that what the delta H of formation is also different for gases and liquids?
Not necessarily because of the entropy, because it takes more at that same temperature to get it to go there, right? Or less, depending on which direction they're going. Okay, so the entropy of a gas is the greatest, entropy of liquids, then the middle, and entropy of a solid is the lowest relative to the same thing in each of the physical states. That's it. The next one, and this one was a little bit maybe obscure in terms of the term molecular complexity. That just means how many things are connected in the compound. The more things you have, the more complex it is. Which should make sense, right? Because if I said I have this, and forget about just the focus of this was the dissolving it, right? So let's forget about dissolving it and just say I have NaCl. And if I could break up NaCl in some way, I can get 2 things from it, 2 particles, right?
Mm-hmm.
And then if I have C6H12O6, if I were to find a way to break that up, how many different things can I get?
24.
Which one's going to give me more entropy?
The top one?
The thing with more.
Yeah.
This is more molecular complex, is the point. Okay. That's what I mean by molecular complexity. And let's take a look at here. So I have argon and NO. if I split argon, can I do that? Is it just argon? Can I separate N and O?
Yes.
I get two things versus one. This has a greater molecular complexity,
Better entropy.
and therefore this should have a greater entropy,
Right.
and it does. The other thing I'm going to point out here, though, is that the molar mass of the argon is actually greater than the NO. Yet, the molecular complexity outweighs the molar mass, and therefore overall has a greater entropy. So then if I was determining between molar mass and molecular complexity is going to take precedence over the molar mass for the amount of entropy. It's going to mean you'll have an increased entropy regardless of the molar mass. Assuming that the molar mass isn't so large and only a very minor molecular complexity. Okay, so here you can see this is about 40 grams per mole for argon, and these two things combined are about 30 grams per mole, yet they have over 50 more joules per mole Kelvin of entropy. So you get the molecular complexity is going to outweigh the molar mass in terms of entropy.
So for diatomic elements, how would that impact for molecular complexity? Would that be considered like more
Yes,
complex?
absolutely.
So when you're talking about molar mass, you have to think about that too, I guess, right?
But once again, if you're just looking at Br2 versus argon, then the molecular complexity will outweigh. You would expect that the entropy would be higher if you didn't know any numbers, which is essentially all I'm really discussing.
Does it also outweigh the physical states, or just depends?
No, not necessarily. But I won't give you a mixture of that because that's too hard to determine just by this crude method. There I need to see the entropies in order to say which one would be more or less, right? Because there, it matters which different state you're referencing and how much molecular complexity you're dealing with. And there is no standard way to assess that, right? Usually, the physical state in the gas is going to outweigh the others, and any molecular complexity most likely, right? However, not necessarily liquid to solid. There, it's not as big of a difference, and therefore maybe the molecular complexity would be on top of, in terms of the entropy, you would gain more entropy. But once again, it depends on how much we're talking about, which substances we're talking about, et cetera. Right? That's a little bit more challenging to assess that way. Okay, here, what do I have here? Carbon monoxide and C2H4. They're both gases here, which is important. Here we're just saying, okay, the molar mass is about the same, yet there's a lot more molecular complexity on the C2H4, and therefore there is more entropy associated with it. Okay, lastly, which I already pointed out, the fourth one was the, if I go back here, let me make sure we're doing the final one, I think. The extent of dissolution is really just what I put up over here, which is the sodium chloride, adding water, going to sodium plus, and chloride minus. It's just the dissociation of the compounds. Okay, so there's no extra slide related to that. Okay, so let's rank these based on those ideas here, right? We're talking about molar mass, we're talking about physical state, and we're talking about molecular complexity for the most part. Based on those, let's rank these in order of increasing standard molar entropy. What would you expect? Is there any difference in molecular complexity between any of them?
No.
And the states are all the same, which they should be, because that's more different. So what are we really looking at here?
So is I is the greatest one?
Molar mass,
Right.
So which one is the smallest? And then, or the lowest molar mass, smallest?
CL.
So F2, then?
Yeah. CL.
CL2, then
BR.
BR2.
I.
Pretty easy, right?
Yeah.
Increases entropy, molar mass. Big deal.
Given the same complexity.
Now, oh, look at this.
Mhm.
A little bit different. We're going to assume they're all gases, okay, because we don't want to mix up the states as brought up earlier.
Helium.
So what
Helium.
would be here the major criteria?
Molecular complexity.
So the lowest
molecular
one,
complexity. So which ones have the least amount of molecular complexity?
helium,
Neon and helium. Which one is lower in molar mass?
helium.
So helium would be first,
Then
then
neon.
neon.
Yeah.
Okay.
And then
Molecular complexity next. I have four
SO2.
things, three things.
Yeah,
Maybe
that
that
one.
goes here.
Yeah,
Then this one, and then this.
yeah.
No problem.
No,
Pretty easy.
you can put 2 of those in the exam.
So I hear one vote for having 2 multiple choice questions related to this. Is that what I'm hearing?
More than that.
We should make up about 30% of the exam.
Now we're talking.
Just the first one. Not the second one's fine, like the first one.
You probably will get one though, which
Just
should be
one?
some percentage, right?
Probably.
The problem is on an exam, you're going to see all of these weird answers that are all going to look right.
Yeah.
So how do you avoid
Yeah.
how do you avoid that?
Yeah.
You cross them out.
Solve it on the
Take a step
side
back,
and then just
yeah.
match it. Don't try to match it with these things so they all start to look right.
Yeah.
Okay, now, oh, this is, wow, okay. Entropy usually, okay. If you recall on Tuesday, this is what I brought up early on. And that's if I'm looking at a chemical reaction and, or just a system, then where I have a molecule that's broken into 2 or more smaller ones, sort of like what I did here, sodium chloride, this isn't necessarily a reaction, this is just, we'll call it a system. It just dissolves and separates the sodium ion. This here is going to increase entropy. So if I see this, or if I see a decomposition or something like that, right, then I automatically know that the entropy increased going this direction.
Right.
That's it. Same thing with the B is just the number of moles. If I have gases and the moles of the gas are greater on one side or the other, if they're greater on the right side, it means I increase entropy. If they're greater on the left side, it means I decrease entropy.
Would you also see that by the phase changes though? Like there's an example that they gave us, I don't know, I think it's maybe the next slide, but it goes from a solid to a liquid to a gas. So that would also show you by the phase changes.
You mean this?
Oh, no, it's forward. They
This
have
thing?
it on our. or
This is
like-
the idea you're talking about though, right?
Yeah.
Yeah.
Except for the thing with this is this really on there?
No, I was talking about a problem in a future slide.
Okay.
It's like the next slide, that's just on our paper.
Yeah. We can definitely look at it that way as well. But what I'm really pointing out is these are the ways that you could quickly look at a system or a chemical reaction and identify if the entropy increased or not, right? So that's something that you will do in a couple problems, so keep that in mind. But we talked about this on Tuesday, I'm just re-bringing it up, it's coming back up here. Then it goes from this to the standard state of entropy changes in a reaction can be calculated from the standard entropies of the reactions and products. And all this is the same thing you did with delta H. And once again, you could do this with delta G. Nothing different than your knowledge base currently. Nothing at all. It's just this. Delta S, this is standard state. Some of them, the products, using the moles in the balanced chemical reaction minus the reactants, using the moles in the balanced chemical equation. Nothing to, what you need to know here though, you need to have a chart or you need to have the numbers in order to do it, that's it. Okay. Nothing new. So let's take a look here. Oh, whoops. It goes into, why did it go from here to there? Okay.
It's just examples.
So for each pair of substances, choose the one with the higher expected value of standard molar entropy. Okay, this versus this is the same thing we already did,
Yeah.
right? Molecular complexity, whatever. Okay, here you have liquid and a gas of the same thing, so it's got to be the gas. Let's walk through this real quick. This is molecular complexity, and this one molecular complexity, okay. All right, I don't know why this is here, this probably should come out. Okay, this is what should have been here, right? Is now let's just do a quick example of solving for the delta S, standard state delta S of a reaction. So first it says, well, predict the sign here. So I guess we're not going to actually solve it just yet. Can we predict the sign here?
Yes.
Yes. So this is 1 and 3 moles,
Yeah.
and this is 1 mole, so it went down. Okay, no big deal. Is everybody okay with that? Okay. Another one? Okay, what about this one?
You can't find it because it has an equal number.
That would be down.
Yeah, you don't know. You simply don't know.
It's an equal number.
But doesn't it increase when a molecule is broken into two or more?
So if I break this into 2 and that into 2, I get 4. I break 2 of these into 2, I get 4.
Yeah,
Molecular complexity is nothing, I don't know anything here. So I'd say I don't know.
yeah.
Oh, good. Right, that's good. That's okay though. But then can you figure it out? So, okay, how would I figure this out? This is an interesting thing to talk about. How would I figure this out? Yeah, I'd have to know the delta S, the standard state delta S of each one of these. I'd say 2 times this, right, minus this plus this. And whatever that gave me, then if it's a positive or negative, so in other words, I could figure it out if I had the delta S's of each one. Okay. But just looking at it, I can't. What about this one? I go from 1
Negative.
Oh, no,
to
negative.
2.
No,
Oh, that's one, the other one is solid.
Oh,
Yeah.
solid.
Yeah.
So it becomes positive. See how
Positive.
easy it is to get tricked there though.
There's only
Understand
one
states.
gas count. Solid don't count.
Solid doesn't
Oh.
do much, right?
Mm-mm.
Okay. So we're talking about the moles of gases. So just to make sure, when you go back to here, reaction in which there is an increase in moles of a
Gas.
gas, right? So I'm now correlating. I know when I say this, it seems no big deal, but when we actually put it into practice, we got to make sure what each thing means. So make sure that that's clear. Okay, good. So this is no problem now. Okay. Now we get to do what really I thought we were already going to do, since we already knew those things, right? We've done those before. I don't get it. Okay, so I have this here, and here are my delta H of standard formation of each one of these things.
Right, standard, yeah.
Yeah. So if I had these in that one that was undetermined, right? So here I could say 4, 5 is 9, 4 and 6 is 10. The entropy should be positive. I already know that. Even though if it was 9 and 9, I wouldn't know that, just like that middle example on the last one. So if I had these numbers, I could then figure it out, right? But in this case, by the way, knowing that it's positive, that's a pretty valuable thing here, right?
Yeah, because if you get negative.
Yeah, because if you get, exactly, absolutely.
So that one is positive?
Right? 4 and 5 are 9,
Mhm.
4 and 6 are 10. Entropy should go up.
Yeah. that's
The
positive.
delta S should be positive here.
And then in math is 1.6 where we get behind.
So then I use this, right? Same thing we did with delta H. Remember, this is kind of tricky though. One thing I want to point out here, when you're so I'm looking at the product, so I'm saying 6 times this plus 4 times that,
Yeah.
minus bracket, minus then bracket this. 5 times this plus 4 times that. If I don't bracket it, then I'd say minus 4 times this minus 5 times that.
Yeah.
Putting that bracket so that you separate this minus sign from the whole thing, then I could add these together and use the minus at the end. Just make sure you don't get mixed up in that. So here I get this and this. Here's what I mean by the bracket here. If I don't put the bracket here, then I'd have to say minus this, is what I'm saying. But with the bracket, I could leave the minus here, just add them together, the whole thing will be negative. Okay? And then I get this, make sure these are all the same units, obviously, and I put those together, and I get, oh, look at that, a positive number. Good. If this came out negative, that means you did something awkward in here, then you just correct it. No big deal. So this is my delta S under standard state conditions. It's okay. Like I said, this is all something you've done before, so I don't want to spend. You did the same thing with delta H's. You can also do what? The same thing with delta G's. Right? So you learn this with delta H's in 101. I just introduced delta S's, same exact thing, and I'm now saying you could also do it with delta H's. Okay. Okay. Which is what we're doing here. Well, it's at least suggesting that you can do it with delta G here, and I think we'll do an example, but the way to get the delta H as a standard state is like this. The way to get the delta S as a standard state is like this. One way to get the delta G's of standard state is like this. What's another way?
Using the
Yeah, Gibbs free energy equation, right?
yeah,
If I had the standard state of the delta H and the standard state of the delta S,
right.
well, then I get this. I get the delta G also,
Just subtract, yeah.
right? What's another way I can get all three?
Using S of the universe?
So this is kind of a little bit more abstract because of how I'm stating it and where it's being placed.
Say where they're all equal to each other?
We did something called Hess's law, right?
Oh,
What was that?
Some of the elementary reactions equals the.
All the elementary reactions, and then you get a bunch of reactions, let's just say.
right.
And
Step by
you
step.
get a final reaction where things cancel out.
Right.
And if you have the delta H's of each one, you make the adjustments. You remember
Oh, yeah, you
Nathan
gotta-
came in and gave this little talk? And then you make the adjustments, and then you add all the delta H's together, you can get the delta H, right?
Mhm. You have
Can
to
I do that with delta S's and delta G's too?
switch them and.
Right?
Yeah.
Why not? So I could do that with those as well. So I could solve for the delta H, delta S in two ways. I could solve for the delta G in how many ways? Three. And those are and that's what this is saying here. I can calculate the delta G in three different ways, and therefore I could also calculate the spontaneity in how many ways? See, these are exactly the kind of questions that get you lost, right? There are actually four, right? Three of the delta G's, but what about the delta S of the universe? That'd be the fourth way. You see how, right? So, but thinking about this, that's exactly the kind of question that you get often. You're like, how did I miss that? I didn't, because it led you in a certain way. Don't be led that way. Think about it and then make the assessment, right, of what it should be. So there are four different potential ways of determining spontaneity, but three different ways of determining delta G's. Okay, that you know, right? Okay. So, I guess I'm going to lay out the methods for solving for delta G, calculated through delta H and delta S, calculated from just the delta G's of formation. Remember, those are all formation values going one way. And lastly, through delta G values of known parts of the equation to get the whole equation, or this would be similar to Hess's law kind of thing. Okay, so I guess we're going to do them. Not too bad so far? Good. When I first taught this chapter, maybe 12, 14 years ago, whatever it was, it's so hard to get the information across in a way that was understandable. Everybody just stared at me, and you know it. And over time, you start to find creative ways and new and unique ways to explain things to make it easier. And when I see like the yes and the shaking the heads and the eyes are like excited, I know that it's working. It's a progression of my ability to get the information across, which is hard to do. It's not as easy as you would think. It's, the tendency is to say, okay, I don't want to miss anything here, but then adding too many things, convolutes it. It makes it more congested and less understandable for the level that's needed. Of course, you need to make sure you give enough so that you can accomplish whatever you want within this realm. You might need to know a little bit more if you're in physics, for example, or something like that. But how much do you need to know here, and how to minimize the effort it takes for you to understand it? Okay, method one, just doing this. Let's just move through this, and we're using this, that's all. But you notice now we're just doing these in standard states. That's it. So I can get those from a table. Okay, so here, I know somebody's going to ask me this question, and if you know me by now, not only from this semester, but previous semesters if you've taken me, clearly I'm not going to have you memorize anything related to this, okay? So you don't need to ask me that, you don't need to worry about that, you don't need to write these out into your, page of notes for you don't need to memorize these kinds of things. I'll always tell you what you knew, and there's no way I'd expect you to memorize the whole chart of delta H's and delta G's and delta S's and whatever else, especially when there are charts available. That doesn't make any sense. Okay, so I'm giving you this here, and this for this example, I see this equation here. This is just to make it a little bit easier. And that's because you're looking at just O2 here. And essentially, what am I going to do here? What am I going to do with this? In your books, you have a chart like this, right? You have an appendix or something. You might even have a chart in your chapter of this, and in the back, you have a more expanded chart of all of these things.
Oh, so they want
What do
a
they
standard-
show?
A standard?
So I see this, you see this kind of thing here, you see this here. Is there something else? Has anybody looked at this or seen it in a book?
I
Or?
haven't seen it.
I've already said it multiple times, but
That's standards.
there's a delta G there too.
Okay.
So, right. So I would argue that if there's a delta D there, there's no way I'd use this method unless I just automatically knew those numbers. Because what do I have to do? I have to do the product minus sum of the product minus sum of the reactants for each one in order to get the delta H of this and then the delta S of this and then to put it into my Gibbs free energy. But if I have the delta G, I only need to do it once for the delta G. Does that make sense?
Yeah.
Okay, good. So here I'm just doing the delta H. This is the sum of the products minus the sum of the reactants. So this is only one product here, delta H of SO3 has a gap. Make sure when you read these charts, identify the physical state, because those do change in here. This particular one, I'm giving you exactly what's given here, so it's not a big deal. But when you actually have them, you may see a bigger one. It'll say SO3 liquid, SO3 solid, SO3 gas, and each one will have different numbers associated with it. Keep that in mind. Okay. So then I have the O2 for the delta H is 0. Okay, there's my 0. SO2, there's only one of them, and it's minus 296.8. That's a plus. That's a negative, makes a positive. So I'll overall have a negative delta H, which gives me this. No big deal there, right? Same kind of thing we've done over and over. Now I do the same thing with delta S. By the way, since I'm using half here, I'm going to use half there, make sure that's clear. If I just put this, if I multiplied everything by 2, I'd go 2, 2, 2, 1, 2, and then I'd have to do 2 here, 2, etc. I'd end up with the same thing, but just stick with whatever they have here. And then this is the SO2, which would be right there. Put those together, and I get negative 94.0 joules per Kelvin. The first thing I should note is that this is in kilojoules, this is in joules. I have to make that correction. The second thing I should note is what? What am I missing here in order to solve?
Temperature,
Yeah.
but it's standard.
But it's standard, so it's 298.
298.
I want you to remember that. Under the standard conditions, it's 298, which is also 25 degrees Celsius. So even though it's not stated here, since you're using the standards here, then you should automatically know that at 298 is the temperature. Okay. So now I just plug them in. There's my 298, and I get negative 79 kilojoules, which means what? It's spontaneous. Absolutely. This is a spontaneous reaction.
You said if we had the delta G's, so we just do one equation. How
Well, you
is
do the
that?
same thing with just the delta G.
Okay. With the, right.
If I have the delta G's, I do this, instead of doing delta H and delta S and then doing this, I could just do one of these, which would just be delta G.
Products minus the reaction.
Yeah, same thing.
Okay.
Delta H this way, delta S this way, delta G this way. I could do any of them if I have them.
Yeah. Okay.
Right, so if I had the delta G next to it, would I rather do all of this or just one delta G?
One delta.
Yeah, right, that's all I'm saying. Which I'm sure is going to be method 2, I think, right? This is method 1, that will be method 2.
Okay.
Okay. But I could, but if I gave you, say, only this, then you can't, there is no delta G, so you have to do it this way. Or if I just gave you the number of delta, if I gave you a number for delta H here, and then a number for delta S for this, then you would just use that. You wouldn't want to, you wouldn't have to go. It depends what you were given, what you can use. The main point here is that there are multiple ways to do it. Okay. Bless you. What do I have here? Okay, so here they're saying, so appendix 2A, I guess, in your textbook, gives the delta H's, it says to calculate the delta H and the delta S and the delta G at 25 degrees for the reaction below. Is the reaction spontaneous? If not, what would a change in temperature, if not, would a change in temperature make it spontaneous? So, this is an interesting one. How this is stated would mean that if I opened up appendix 2A, I get delta H, delta S, delta G. I solve for delta G, and delta G is positive, okay, which is what this implies will happen. Then I would say, okay, what can I do to determine if if a temperature change would make it spontaneous?
You would have to see the changes, you would have to see the signs of S and G, so then you could see from the chart. that
For the
we had
sizes?
before.
What I would say is I would then do the delta S and the delta H, solve for the delta G in the context of delta H minus T delta S, set the delta G to 0, and then solve for T. But you notice if I just started with delta G alone and did it, then I could only determine plus or minus, spontaneous or not spontaneous. If it's not spontaneous, and now I want to know what temperature it would be, I'd have to go back through all the rest.
This is the 2A. That's the 2A. In this textbook.
Just go to whatever it is, what's below it. There it is.
The
This
2B.
says 2B in this case, in this one. So different text depending, I guess.
Okay.
Either way, go to the appendix 2A where it shows the thermodynamic quantities at standard state.
Yeah,
Whatever that is.
gives you the Gibbs as well.
Yeah, that's what it has. It has the Gibbs.
Uh-huh.
So that's what I'm saying. So my first instinct would be to do the delta G. If in this case, though, actually I probably wouldn't. This is telling you to calculate those other components, so you have to calculate them all.
Mhm.
So in that, if it didn't ask that, if I just said using appendix 2B or whatever it is,
Yeah.
calculate the delta G at 25 degrees Celsius. And then if I continue, if not, is this reaction spontaneous? If not, would a change in temperature make it spontaneous?
Mm-hmm.
See, there I'm not specifically stating to solve for delta S and delta H.
Right.
And so in this case, you guys can do this. So whatever your appendix is, or you can just go online. Just look up standard state conditions for thermodynamic properties, right? If you do that, you don't have to use the textbook. Just use whatever you find. It should be good enough. And you can solve this. Is this okay? Everybody know how to solve this? Yeah. Okay, good. Okay, method 2. I want to get through at least through the methods here. So here it's just, it's the same thing. Now you're just solving for the delta G's, not the delta S's and the delta H's, and then through that. Okay, so what do I want here? Free energy. So delta G of formation, standard state. Just make sure we already talked about this. 1 mole of compounding, standard state. Free energies of formation. Pure elements in their standard state is 0. Okay. So let's just do this. It's really just this. This is method 2. We've already talked a lot about this.
Yeah.
So let's just solve one, make sure we understand it. So that I got this out of the book here. I look up each one of these, make sure you look, you find them. Or I could just give you this like this. It could be either one, right? And then I just solve the delta G, right? So it's 2 times this, plus this, minus this, which is a 0, plus this. So this gives me a positive over here. This overall is going to be a negative. And looking at it, just so before we go any further, we can't tell by moles of gas or anything here. One thing, 2 things, and 1 thing, so 3 things. I would expect that the entropy went up in the system, but that wouldn't tell me if it was spontaneous or not. So I can't really determine that. So let's just solve for it. And I get negative 62.8 kilojoules. That's right, so it is spontaneous. That's what that would tell me. But the main point here is I solve for delta G in a different way, which is the same way you did for the S and the H's and whatever else.
Yeah.
All right, that's all I'm showing. That's all I'm pointing out here. It's the potential. I guess you can call it a different method. We're going to do the same thing again. So let's just move through this pretty quickly. There's no reason to. This becomes positive for delta G and therefore non-spontaneous. Is there anything I want to point out here? No, you guys already know how to do this, right? There's nothing new here.
Yeah.
Right, okay, there's nothing unique to this, okay. Good. Again, you guys can do that one at home. If you have any problems or want to know the answer, just ask me. Nobody needs to see that again, right?
Could you just show us the answers so we could,
I think the answer is no.
oh, never mind.
Method 3. Okay, this is kind of interesting. Let's finish. This will finish up. I think this is a good place to stop after this, because then we're going to get into some slightly different things. I'll just bring up the concept of different pressures at non-standard states. Because what is the pressure at standard states that we're assuming here?
118.
Okay, so that's the assumption here, which is not the case necessarily in reality. So let's finish up this. This is the third method. This is the, yeah, that's what remember I brought that up earlier. That's exactly right. So you guys can read all this. There's no big deal to any of this. If I have these things here, known delta G's of these intermediate reactions, and I have the total reaction here, I can also solve for delta G the same way we did before, right? So the first thing is I have to coordinate where everything is. C3H8 is on this side, so I flip this. If I flip that, the sign changes. Then that's making sense?
Yeah.
Over here I have 1C, so I need 3, so I multiply this by 3 across. This becomes times 3. Over here I multiply by 2, and that would be 2. So flip it, bless you. Multiply by 3, and multiply by 2. Now I add those together, I get my delta G. That's the third method. Once again, nothing new there. Right? People like this. And that's it. Negative 23 kilojoules, that's the delta G. So that's another way to do it. Depending on what you're given, you use what you have and then you solve. You can solve for delta G. You can call it 3 methods. So the reason why I hesitate and why I have a problem and presenting it this way, this is how it's presented. It's also how it's presented in the book, I think. But for me, I don't look at it as 3 ways. I look at what I have and then I solve accordingly. Right? So I don't sit there and go, okay, this is method 2, I need to use method 2. That's just an odd way to think about things, right?
Yeah.
Even though the first time you're learning it, those are sometimes pretty good, but in this case, these are all 3 things that you've already learned. So there's no reason to define them that way, other than there are multiple ways to do it. These are the different ways you do it, depending on what you're given in the problem, solve for it accordingly. That's, I think, the best way to introduce it. When we're looking at forming Lewis structures and VSEPR, it is kind of good to have, I don't think of it that way as step 1, step 2, step 3, but in that case, it is good to follow those steps to keep you in line so you don't forget something along the way. So that's where defining methods or steps are relevant. But then as you get comfortable and do it over time, then you sort of just get rid of those things. You don't think about it that way anymore. And thinking about, what's that? Yeah, it's good initially. But in this case, these are not, it's not like I'm just now introducing all of these as new methods and therefore let's separate them. It's just whatever you have, you're given, if there's the easiest way you can solve for it based on the material you're given, that's how you do it. If you're in a laboratory, that's how you unfold and solve for something. Okay. So let's do one more of these here. What do I have here? Okay. I'm solving for this. I could give you this and solve for one of those too, right?
Yeah.
Okay, keep that in mind. So here, what is it? So I flip this, and that gives me the right. So I flip that, becomes plus. What do I do here? I multiply by 3, and that becomes that times 3. Okay. And then you solve for it, then you just 1 plus the other. No big deal. That one's easy. Or it's easier than the last one, which is still not that hard. Is that okay? Anybody unclear of this? Nothing new here. Just you're using different terms. Instead of delta H was how you saw it, you're now doing it with delta G's. Okay. Okay, good. Now, I want to finish off with just a few slides before and kind of introduce the non-standard state concept. Because then we're going to go through a couple more mathematical manipulations and calculations that are in relationship to equilibrium constant, delta G's, and things of that nature in non-standard state conditions, which are not going to be overly challenging, but I don't want to add too much at one time since we have the classroom time. So first on this is something I talked about before. Then after you read through this, remember what I said, if delta G is negative, that means it's a spontaneous reaction. Mm-hmm. The amount of energy that comes off of that is called Gibbs free energy. That means that you have that as free energy. You could harness that free energy to do work on something. And that's something I talked about at the very beginning today because I was hoping we can get this far. And that's essentially what this is. A spontaneous reaction, the energy that's gained, which is why it's called Gibbs free energy, can be harnessed and put in to do work of something. Is that okay? Okay. And that would just be work. So you would define that as if I were to take all of the energy I got and move it into doing some kind of work without losing any of that energy, then it would be the maximum amount of work that I could do from that reaction. Okay. But of course, in reality, you can't harness all of it. You're going to lose some. Okay. So that's all this next stuff is going to be about. So the maximum amount of energy available or free to do work would just be W max. No big deal.
That's within the
Within the
reaction.
system,
Right.
where you have negative delta G, the amount of that negative delta G,
Can be
if you
used,
could
yeah.
take all of that and move it into work, now you've got your work, your max work. That's the max amount of work you can do based on that amount of energy given from that spontaneous process.
No.
And so that's just that's an ideal situation. Completely converted to useful work. Real situation, it's converted into useful work and what else? Entropy, right? It's converted into useful work and some entropy. So this is the amount of energy lost that would reduce the amount of delta G you're using for work. So putting that just in some practical context, you could do all the reading here. You look here, you have a battery. Battery produces some spontaneous reaction. It moves through these lines, and you end up doing work. The work is that the motor it does something, right? It spins, it puts out air, heat, whatever. And in that process, if you had all the delta G that you're getting from here going into here, then you'd get your maximum amount of work out of the motor. Okay. In reality, you're going to lose some out here through the lines, and that loss is going off into the surroundings and therefore being used as entropy, and so you're not getting the maximum work in here. It's very similar to if you take your electricity, right? You have an energy source. You turn on your electricity moves through.
Yeah.
Clearly, all of that electricity is not being used when you turn on your light. In fact, not a lot at all. You're losing a lot of work along the way through there. That's why it's not very efficient. It's also why it costs more. Right?
The
Is that
lines
you're
and-
paying for that lost energy, essentially,
true.
as well as the energy you're getting.
That's why you pay even when you're not home.
That's right. You'll find that, especially here in LA, they'll find all kinds of ways that you'll pay for everything. You'll pay when you use water. You'll pay when you get rid of water. You'll pay when if you wanted to use buckets at the river. They'll find a way to make you pay. So that's all this is. That puts the free energy into context, I think, right? Is that
Yeah.
okay?
When you
Now,
die,
just to close up a couple more things up, I just want to introduce now the non-standard state. Okay. So in what we talked about up to now, with the charts in the back and things like that, we're looking at standard state conditions, which were already defined, 25 degrees Celsius, et cetera. But a lot of times, that's not the case, right? So we're looking at non-standard states, let's say here in the classroom or at home, right? So it's not just, are we at 25 degrees Celsius right now? Are we at 1 atm of pressure?
No.
No. And so that has to be accounted for if I want to determine whether or not something is going to be spontaneous under those non-standard state conditions, right? Because the spontaneity was only based on those conditions. Right, everybody see that?
Yeah.
That's an important, that's what I wanted. So now we do have a way to make adjustments to the standard state conditions by accounting for those differences in terms of pressure and temperature, and therefore we could determine whether something would be spontaneous, maybe more at a more practical situation like in the classroom or at home, maybe water evaporating or condensing or whatever else. Does that make sense?
Mm-hmm.
Okay. So this is just going to tell you everything I just said. You know, why is it spilled and it evaporates spontaneously, blah, blah, blah. And ultimately what I want to get to is this. So this is the non-standard state Gibbs free energy to account for all those other things like different pressures at different temperatures, et cetera. So what I have here is I have the delta G that is the non-standard state is equal to the delta G at standard state, plus the add-on. Remember I mentioned this earlier about the way we made adjustments for ideal and non-ideal gases? That's how I think about this, right? So here's my standard, and then here's my add-on, right? In order to get the actual. It's just one way, it's just a more comfortable way to adjust to something that's not a standard state that you guys have already learned. So here's my standard state for whatever that thing may be. I have my RT, and the R is the universal gas constant. In this case, I'm using 8.314, which is joules per mole K because of the units. So it's not the 0.0821, right? All that difference is what? Yes. So I'm just changing the units here in order to get that deal. And then what's that? That should look familiar. My reaction quotient, absolutely. So remember we looked at that equilibrium thing, and at the bottom was sort of like potential energy at its lowest. That's where you have Gibbs free energy at 0, right? And the Q, when we learned about Q in equilibriums, it told us where we were relative to that point. And that point is K, which means that we could relate this to K also, right? Which is interesting, because we will. If I relate this to K, then this is going to equal what? 0. This will be 0 if this is K. Can I then solve for K? And that's what we're going to look at how to manipulate this equation. Okay, so this is just the thermodynamic reaction quotient, which will tell us if I'm moving this way and I'm above the K, then my spontaneity would go down. If I'm past the K, then my spontaneity is, now it's non-spontaneous, but it would be spontaneous going back the other way. Okay, and I'll leave you with that so that when we come back, we'll finish up about 10 to 15 slides of this, and we'll probably start the last chapter on Tuesday. And on Tuesday, what to do? The take-home exam. Okay, and if you were not here on Tuesday, you can come to my office right now. I'll give you an exam, but that now is still due Tuesday. Right? You don't now have extra time because you didn't